Hello, everybody. Welcome back to the Dirt Talk Podcast Monday edition. Today, we're going to do a deep dive into a project we recently got to visit ourselves in Virginia with Garney, the leading wastewater contractor in America that we've been fortunate enough to develop a great relationship with over the past few years. So to get right into this project, and before I do, we have a video on this entire project. So if you want to see how all of this came together, everything I'm explaining, go to YouTube, search Aaron Witt. You'll find it. Check it out. It's fantastic. So this is a big deal. We're going to start with water and wastewater. We all use water every day. If we didn't, we would perish. And we all discard wastewater when we go to the bathroom, wash our dishes, shower, etc. All of that combines to generate wastewater. And that's when water districts come into play. They not just support humanity by extracting water from the environment, purifying it, then supplying it to our homes, but they collect the wastewater, treat it, discard it accordingly as well. This happens in every large city everywhere around the world. It's a really, really big deal. And sanitation, this is why humanity is a large reason why humanity has done so well over the past few centuries, is because we don't have these diseases going around because we're managing our wastewater accordingly. Most of it's attributed to vaccines, modern medicine, etc., but most of it's really just down to we're not swimming in our own poo anymore these days. So this brings me to the Hampton Roads Sanitation District, also known as HRSD. This sanitation district serves nearly 2 million people around the Chesapeake Bay area and can treat an astonishing 225 million gallons of water every day, which is wild. I was looking at that. I was like, is that a misprint? No, that's every day. It's amazing. In the Chesapeake Bay, this is a really critical area for a few different reasons. One, it's home to the world's largest navy, also home to the Atlantic Fleet. It's also, I believe, one of the largest shipbuilding areas in the world. And it provides $100 billion in economic value annually and is also America's largest estuary. So really, really big deal. This is a very important area on the East Coast. But there are some challenges here. First, the area relies on the Potomac aquifer, which contains trillions of gallons of pressurized water. But due to the surrounding geology, the aquifer cannot recharge naturally to match consumption, making the region susceptible to settlement and saltwater intrusion. So some aquifers can recharge naturally. You can level out, based on what's going out. You can replace that so nothing happens underground. With this aquifer, that's not the case. So it allows salt water to potentially penetrate the aquifer, which is a problem because it makes the drinking water salty, and it can lead to settlement. So second, as well, HRSD currently discharges highly treated wastewater into the bay, which is typical best practice nationwide. And while this water meets all of the EPA standards, Environmental Protection Agency standards, this water can contain nutrients that can affect the ecology. So, how does HRSD serve the area's growing population while improving the bay's water quality and health? That is where SWIFT, or the Sustainable Water Initiative for Tomorrow, comes into play. And that is what all of this is about. So this is a multi-year, multi-billion-dollar infrastructure investment aiming to put tens of millions of gallons of highly treated wastewater through a secondary advanced water treatment process to create water matching the existing aquifer. Then they'll recharge the aquifer using wells carrying the drinking quality water up to 2,000 feet below the surface. And if you want to think about this as a closed loop, they're pumping water out of the aquifer, they're treating it. They are then using it, throughout neighborhoods, etc. Everybody's showering, doing their dishes. That water is discarded into the wastewater system. Then Swift will treat that wastewater into water that matches chemically the water within the aquifer through this amazing system we'll explain in a moment. And then they'll pump that water back into the aquifer to recharge it, which allows for water into the future. So not only are they not discarding that water anymore, but they're recharging the aquifer to allow for water well into the future. It's a closed loop. It's absolutely spectacular. I had no idea this was possible until we visited this project. So this is not theory. It's happening right now, as I've alluded to. So let's get into the construction part of the program. First up, we are starting on the Newport News side of the James River. So we have Norfolk down basically south, then across the James River, we have Newport News. So it's separated by that river, which then feeds into Chesapeake Bay to the east, which is then feeds into the Atlantic Ocean further to the east. Now, there's a treatment plant across the river, but rather than upgrade that plant, HRSD determined the best thing to do was to send the wastewater they're collecting from Newport News to the larger Nansemond treatment plant on the south side of the river. So they're going to, instead of expanding the existing old treatment plant on the north side of the river, they're just going to say, hey, we're going to collect all of that wastewater, and we're going to send it across the river to a much larger plant that can much more efficiently process this wastewater. But how the heck do you get tens of millions of gallons of wastewater across a river that's not only a few miles wide, but also one of the nation's biggest shipping channels? This is when a pipeline comes into play, of course. Garney, they installed the first portion of the pipeline underneath the shipping channel via directional drilling, which earned themselves a world record, and I'll explain all that in a moment. Then, once they're across the shipping channel, they can lay the remainder of the pipeline via cut and cover, which is what they're working on currently. Then, on land, Garney must open cut some more pipe to then reach the plant. And now we've got to the Nansemond treatment plant, an existing water treatment plant, which currently processes about 30 million gallons of wastewater every day. However, with this additional wastewater flowing in, Garney must increase its capacity to 50 million gallons per day without disrupting existing plant operations to accommodate that additional flow. And then finally, they will build the new Swift plant, which will be modeled after the current 1 million gallon per day experimental plant that they have, the research facility that they've created, and will then recharge that water into wells throughout the property. So, going back to the beginning, across the James River, as mentioned, Garney had to install a new pipeline beneath one of the busiest shipping channels, meaning they could not disrupt that shipping channel, and it's also used by the U.S. Navy, so they could not disrupt any kind of activity through that channel with this pipeline construction. Now, how do you do that? Well, you do that. Anybody that knows anything about underground utilities, when you can't disturb the surface, knows that you use directional drilling, which is a magical technology allowing pipeline installation without any impact to the surface, or in this case, the channel. So, directional drilling is similar to traditional drilling for wells or oil, but it's parallel instead of perpendicular to the earth. So you're going with the earth rather than up and down like drilling a well. And to go from A to B, crews set up a directional drill on one side with a reception pit on the other side. The drillers make a pilot hole with a small bit to establish the correct depth and alignment for the drill. They will carefully track the bit as they go, eventually navigating it to point B. So you poke a small hole from A to B using that pilot bore. And once they connect the dots, it's then time to upsize the hole with reaming. So you poke the hole, you poke the hole all the way through, and then crews at point B will attach the first reamer in the reception pit, and that drill will pull that reamer through the hole again, which has a larger diameter than the initial bore. So as the drill pulls it through, it makes the hole bigger, and it upsizes things to get closer to the diameter of the pipe that they have to pull through. And as they're pulling it, they're adding additional drilling steel on that reception side, so that steel through the hole never ceases to be there throughout this process. And to keep the hole open, they're also pumping in a bentonite slurry, and it's injected through the reamer, and that hydrostatic pressure keeps the hole open and pushes the cuttings, the material they're removing, toward the surface. It can be processed, and then that bentonite is recycled back into the hole. So crews repeat this process many times to establish the correct diameter, which is always substantially larger than the pipeline they have to pull through. Finally, we have pullback, and crews assemble, or in this case, fuse the entire pipeline length at the reception end and attach it to the drill. The drill then pulls it through the hole, installing the pipeline under the earth without disturbing anything above. It is spectacular to see. It takes a lot of time and energy to do, but it does not disturb anything above the surface. Again, in this case, the channel itself. Before getting into this project, engineering called for a water-to-water bore because of the length. But after evaluating the options, Garney opted for a water-to-land bore, which put them into world record contention for the length and diameter required. So engineering didn't want to go for that world record. They said, it's a little too far. Let's just go water to water. But when Garney evaluated it, the water closest to the land side is very busy. There's a lot of shipping and other activity on that side, not a lot of room to work. So they just said, hey, we actually think we know we can do this water to land. So let's set up point B on land, removing that bit of uncertainty from the water. So getting into the numbers here, the channel depth is about 70 feet, and the pipeline they installed is below the channel safely at about 170 feet, so 100 feet below the bottom of the channel. The pipeline is 42-inch HDPE, or high-density polyethylene pipe, and the distance of the bore was 5,700 feet, so over a mile. Garney had to prepare both sides for months with a pit and 66-inch conductor casing going in on the land side to get through the soft ground. On the water side, in the middle of the river there, just on the other side of the shipping channel, they built a temporary work platform constructed of driven steel piles topped with structural steel and wood. They installed another 66-inch diameter by 600-foot long conductor casing to reach suitable material. So they built the reception pit, they dug the hole, and then they drove a conductor casing into the earth toward point A, where the drill was out on the water. And this conductor casing got the bore through that soft material into the harder material that was easier to drill. And they did the same thing on the water side. They built that enormous temporary work platform. They hammered in that conductor casing, and that casing then got them through the water, through the soft material on the bottom of the river, and into that harder material they could drill through more effectively. They used the intersect method for drilling, with two drills, one at either end, drilling toward each other. Huxted performed the drilling using real-time positional data to guide the drill heads toward each other, meeting in the middle beneath the channel. So they had a drill at point A and point B. The land drill then followed the water drill to the other side, which then established their pilot hole. Reaming then began with a single drill on land, so they demobed the drill on the water side and kept the drill on land. And they pulled larger reamers through the bore over several weeks, eventually creating a diameter of over 50 inches. So a very, very big bore, 50 inches over a mile long underneath the active shipping channel. And now for pullback, the moment we've all been waiting for. Using a pipe fusion machine on a barge, Garney crews fused all 5,700 feet of HDPE on the water, and then they floated the pipeline in preparation for the pull. So they floated the entire 5,700 feet out into the water before they could pull it. You have to have the entire length fused before you can start pulling. And the challenge for the pull was the force applied to the HDPE, which can break if too high. So to lessen the force applied by the pull on the land side, applied by that drill, Garney brought in a pipe pusher from Germany to help push the pipeline on the water side simultaneously. So you had a drill on the land side, pulling that pipeline through, and as it was pulling, there was a pusher on the water side pushing that pipe from the other side so that the tension on the pipe did not exceed a certain amount of force to ensure that pipeline was good to go as it was installed. On May 1st, 2024, the pullback began with cranes on barges helping to position the pipeline via cradles through the pipe pusher and into that conductor casing on the water side. Over 24 hours of pullback, after over 24 hours of pullback, as they pumped water into the pipeline to prevent buoyancy, they didn't want the pipeline to float, the crews finally achieved a world record pull for HDPE 5,700 feet. It was absolutely spectacular to see this footage. I unfortunately missed what was going on. I was speaking, ironically, at Garney's annual event while they were doing this, but I saw lots of footage, and it was spectacular. So now we are across the active shipping channel, but we're still in the James River. The James River is a few miles wide. We only had to bore under about a mile of it, but there's still quite a bit of pipeline to go that's not in the active shipping channel. And this is when the open cut portion of the work begins. There is a barge with a crew working out there now. Actually, there's three operations. So first we have a barge with a large duty cycle crane, a big clamshell bucket, cutting a majority of the material for the pipeline trench, much like installing pipe on land. You have an excavator that digs the trench, then you lay the pipe, then you backfill. This is all happening, but it's all underwater. So there's a dredging company, a duty cycle crane doing a majority of the excavation out front. Then there's a Liebherr long reach excavator with GPS doing the fine grading, so to speak. They're digging that trench with the GPS, that marine setup that they have to get to that proper elevation. And then they're discarding the spoils alongside the trench. Then we have Garney's work barge that moves along the trench as they lay the pipe. At the front, there is a pipe fusion machine within an enclosed area to control the temperature because it gets quite cold in the winter. This massive fusion machine fuses the HDPE together. It takes about an hour and a half per joint. And what the fusion machine does, if you haven't seen it, it shaves down both sides of the high-density polyethylene pipe so that it's absolutely perfect and smooth. Then it has a plate that it pushes the two pieces of pipe against to heat both sides of the pipe. It's plastic, so it can heat it up. And then it removes the plate and pushes the two pieces of pipe together, fusing those two pieces of pipe, and it lets it cool. And with perfect fusion, that point of fusion is actually materially stronger than the pipe itself. So it's very, very effective. That's happening all on the barge. They're fusing as they go. Then outside of that fusion area, there is a crew working on installing the concrete anchors to the pipeline so the pipeline does not float. They are putting these anchors on every certain amount of feet so that as the barge advances, the pipeline then rests perfectly on the bottom of the trench they have excavated, but it can't be too heavy. They don't want it to sink. It has to be perfectly on grade because they don't want any air within this pipeline. There's no air release across the entire river, so it has to be on a perfect grade as they go. And within this barge as well, on this barge, they have a crane to help the crew move the pieces of pipe, the concrete collars that they're installing on the pipe, etc. And then once the barge advances far enough, another crew comes back in. They backfill on top of that pipeline. That pipeline is at the bottom of the river. Now, after a few months of work, many months of work, Garney will be then across the river. That is when the open cut portion of the program starts up. It's not a giant quantity of open cut, but it's traditional open cut to take the wastewater from the edge of the James River to the Nansemond treatment plant, which is not too far away. Okay, so now the wastewater from Newport News across the river is over to Norfolk, to the Nansemond water treatment plant, to the Norfolk side. Now we have to expand the plant from the current 30 million gallons per day to 50 million gallons of wastewater treated every single day. And how does wastewater treatment work? Well, it's actually very interesting. This is the first time I feel like I've wrapped my head around it. And the best way I can explain it is that it's like a giant aquarium filter, just like the aquarium at my desk. First, there's primary solids, which removes the big stuff called rags in the wastewater business. And yes, this is some of the chunky stuff, and it just does not smell very good. You can imagine how this stuff smells, but you want to get any of the big stuff out using screens. Then we have a primary clarifier, which settles the larger suspended solids within the water. It's similar to how salad dressing settles in the fridge. If you leave your salad dressing alone, you've got the solids that will settle to the bottom. This is the exact same thing that's happening here, just on a much larger scale and stinkier scale. The solids sink to the bottom, which forms a sludge that can be removed, and the remaining liquid moves to the next stage, which is now the PEEQ, or large storage tanks. These are giant concrete tanks that help equalize the flow through the process, especially during large inflow events like heavy rainfall, which is also treated. The water coming into the plant varies. Like I said, if you have a big rainfall event, all of that water is collected with the storm drains. That's considered wastewater. That all goes to the wastewater plant as well. But the plant can only treat a certain amount of gallons every hour, every day. So if more comes in than the plant can treat, this is where it will sit within these tanks before it can move to the next process. It equalizes the flow. Next is the real magic of the wastewater treatment process, the aeration, which aids in biological treatment and the breakdown of remaining organics. So this is where millions and billions and maybe trillions of little biological organisms feast on the organic matter, helping it to decompose. Within these tanks, you'll see bubbles in the water, and that's intentional aeration, which keeps all these little bacteria and organisms happy. And believe it or not, this process does not smell all that much because of more complex processes before this. So this is where the real breakdown biologically happens. This is absolutely where the magic is. And that, after this microscopic feast, almost gets us there. Finally, there's the secondary clarifiers, which allow the remaining solids from the microscopic feast to settle out. And finally, you get what looks like very clear water. Last, before the water is discharged, it goes through a mild chlorine treatment process, which disinfects the water. So that water is then considered highly treated wastewater. It's disinfected. It's been treated to a very high degree, and that is what goes into the bay currently, and that's how most plants across the United States work. But we want to get that highly treated wastewater to match the aquifer absolutely perfectly. And this is where the whole SWIFT thing really starts to take shape. So currently, they have at the same area a research facility which produces 1 million gallons a day to refine the process. All of this needs to be refined, and they've been working on this for years. So many hardworking people behind the scenes, scientists, analyzing how to do this at the 1 million gallon per day scale before they scale it up to an eventual 34 million gallons per day. And so this is where it really starts to go over my head because it's serious science. But ultimately, again, the SWIFT process is to transform highly treated wastewater into drinking quality water with the same chemical composition as the aquifer. It's absolutely spectacular stuff. And as an insight into this process, they first remove very fine sediment. Then they add ozone and allow for further biological treatment, which is similar to the initial treatment process, but at a much more minute and fine level. Then they apply activated carbon, ultraviolet light, and chlorine, which gives us just perfect drinking water with the exact same chemical composition as the aquifer. And then from here, to get it back into the aquifer for recharging, the drilling then comes into play. In the area surrounding the plant, drillers will eventually drill 19 wells, 30 inches in diameter, each about 1,500 feet. And the water will then go into the aquifer via these wells. And they'll space these wells out to maximize recharge. But the water traveling through the earth travels very slow. So it will take years for water to travel only a stone's throw away, just right underneath the treatment plant itself. So that is how you go from wastewater to a recharged aquifer for people to have water well into the future across the Chesapeake Bay area. There was all of this wastewater across Norfolk or across Newport News. All of that is collected. It's pumped across into that HDPE pipeline underneath the shipping channel, underneath the James River. It then travels a little bit across land to the Nansemond treatment plant. Eventually, the treatment plant will be at 50 million gallons of wastewater treatment per day. Then from there, it will flow into the SWIFT plant, which is the fine-tuning process to take that highly treated wastewater and create that perfect water to match the aquifer. And then they will, right underneath the plant, recharge the aquifer and again ensure water for generations. That is the amazing SWIFT project. I really appreciate HRSD having us out. I appreciate Garney for having us out. And like I said, we have a video on this entire thing. We show everything step by step. So if you've not seen it, you can go to YouTube, Aaron Witt, check that video out. We have hundreds of others there for your enjoyment. And we're publishing new videos every week, like we're doing with the podcast, new episodes every week as well. So thank you for listening. If you have comments or things for us to check out into the future, send us an email at dirttalk@billwitt.com. And we will see you on the next one. Stay dirty, everybody.